Take one single dollar, put it in an account that earns 5% a year. Let it compound, quietly, untouched, for 2,000 years. You would end up with more money than the total mass energy of the observable universe. Read that sentence again, because it's not an exaggeration, and it's not a rounding error. $1, 5%, 2,000 years, more value than every star, every planet, every particle of matter and energy that exists, anywhere, in the entire observable cosmos. That number should feel impossible, because in a real sense it is. Nothing in the physical universe grows like that, unchecked, forever. Not bacteria, not stars, not empires. Every real growth process eventually collides with a limit, a wall, a ceiling, a constraint the universe simply won't let it pass. And yet, every retirement calculator, every investing app, every finance influencer casually shows you a smooth, exponential curve climbing up and to the right, as if it could just keep going, forever, untouched by any of the limits that govern literally everything else that exists. So here's the real question this video is going to answer. Is compound interest actually breaking the laws of physics? Or is it revealing something stranger? A genuine blind spot in how the human brain understands growth, time, and limits. Let's find out, carefully, honestly, and with the numbers to back it up. Before we go further, let's be precise, the same way we always try to be on this channel, because a bold title deserves an honest, careful answer, not just a scary number. Compound interest does not literally violate any law of physics. No asset, no bank account, no investment fund has ever actually compounded for 2,000 years without interruption. In the real world, every compounding process runs headlong into constraints. Inflation erodes it, regulation caps it, competition drains it, defaults interrupt it, and something economists call mean reversion, the tendency for extreme growth rates to eventually slow back down, quietly reins it in. So the phrase, breaking the laws of physics, is poetic, not literal. But here's why it's still a genuinely useful, defensible way to frame this topic, rather than empty clickbait. The math of unconstrained compound growth really does produce numbers so large they become physically meaningless, the same way certain equations in physics produce answers that signal you've pushed a model past where it actually applies. Compound interest isn't breaking physics. It's revealing, with startling clarity, exactly where financial math quietly stops describing anything that could exist in the real world, and that boundary turns out to be a genuinely fascinating place to explore. Let's start by clearing up the single most repeated, least verified quote in all of personal finance. You've almost certainly heard this line. Albert Einstein supposedly called compound interest the eighth wonder of the world, and reportedly added that he who understands it, earns it, he who doesn't, pays it. It's quoted in books, seminars, YouTube videos, and finance blogs constantly. Here's the uncomfortable truth. There is no solid historical evidence Einstein ever actually said this. No verified letter, no recorded lecture, no primary source anyone has ever successfully traced back to him. It's almost certainly a misattributed quote, the kind that gets pinned onto a famous, brilliant name, because it lends credibility to an idea people already wanted to believe. But here's what's genuinely interesting about this myth, rather than just debunking it and moving on. The quote persists, decade after decade, precisely because it captures something true about human psychology, even if Einstein never said it. Compound growth is deeply, genuinely counterintuitive to how our brains naturally process numbers. The myth survives because the underlying feeling it describes, that compounding seems almost magical, is completely real, even if the attribution is fake. Here's a fact that surprises almost everyone. Compound interest is not a modern financial invention. It's thousands of years older than banks, older than paper money, older than most of the civilizations we typically think of as ancient. Ancient Mesopotamian and Sumerian civilizations, going back to roughly 2000 BCE, were already using compound-like interest structures in loans of grain, in loans of silver, long before anything resembling a formal financial system existed. Clay tablets from this era, record loan agreements with interest, calculated in ways that mathematically resemble compounding, not simple interest. This detail matters because it reframes compound interest as something closer to a mathematical inevitability that human civilization kept independently rediscovering, rather than a clever modern financial product someone invented to sell you. Whenever humans have loaned resources to each other across time, some version of this exponential structure has tended to emerge, almost as if it's baked into the basic mathematics of value and time itself. Now let's get to the mathematical heart of why this topic connects so directly to physics, and this is where things get genuinely elegant. With continuous compounding, meaning interest calculated not just yearly or monthly, but constantly, at every possible instant, the compound interest formula transforms into A equals P times e to the power of RT. That letter, E, is Euler's number, a fundamental mathematical constant, approximately 2.718. Here's why that single letter matters so much. He isn't just a finance formula's convenient shortcut. It's one of the most fundamental constants in all of mathematics and physics, showing up in radioactive decay equations, in the mathematics describing wave functions in quantum mechanics, in population growth models, in almost every process throughout nature that involves continuous, self-reinforcing change. When your bank account compounds continuously, it is, mathematically, running the exact same equation that describes a radioactive atom decaying, or a quantum wave function evolving over time. That's not a loose metaphor. It's the same constant, doing the same mathematical job, in a completely different physical context. Money and physics aren't just similar here. For this specific piece of math, they're identical. Let's return to that opening number and actually walk through why it's true, because seeing the mechanism makes it land much harder than just hearing the punchline. Start with $1, compounded at 5% annually. After 1 year, you have roughly $1.05. Unremarkable. After 10 years, about $1.60. Still unremarkable. After 100 years, about $131. Getting more interesting. But exponential growth doesn't slow down as the numbers get bigger. It accelerates, in absolute terms, precisely because it's growing. After 500 years, you're in the trillions. After 1,000 years, numbers so large they stop being intuitively meaningful to a human brain at all. And by 2,000 years, you cross a genuinely staggering threshold, a dollar amount larger than physicists' best current estimate of the total mass energy contained in the entire observable universe. Every galaxy, every star, every particle, converted into energy equivalents using Einstein's own mass-energy equivalence. This is exactly why real-world compounding always, eventually, collides with constraints. The math doesn't know when to stop. Reality does the stopping for it, through inflation, regulation, competition, defaults, and the simple fact that no financial institution, no currency, no economic system has ever survived intact for anywhere close to 2,000 uninterrupted years. Here's a mental math shortcut you've probably heard, and a hidden piece of mathematics almost nobody realizes is sitting underneath it. The rule of 72 says, divide 72 by your interest rate, and you'll get a rough estimate of how many years it takes your money to double. At 6%, that's roughly 12 years. At 8%, roughly 9 years. Here's what almost nobody knows. This rule isn't an arbitrary trick. It's derived directly from the natural logarithm of 2, which is approximately 0.693. 72 is simply a convenient, easily divisible approximation of that number, scaled up for practical mental math. And here's the important caveat. This approximation works best in a specific range, roughly 6 to 10% interest. Push it to extreme rates, very low single digits, or very high double-digit rates, and the approximation starts breaking down significantly, drifting further and further from the true, precise doubling time. It's a genuinely useful tool, but like so many of the models we've discussed on this channel, it's an approximation quietly built on assumptions that only hold within a specific, limited range. Here's a trap that catches even experienced investors, and if you watched our video on the Fed and interest rates, this pattern should feel immediately familiar. Compound interest can be negative in real, purchasing power terms, even when the nominal rate you're earning is positive. If your account compounds at 3% annually, but inflation is running at 5%, your money is growing in nominal dollar terms. The number on the screen is getting bigger, while its actual purchasing power is quietly shrinking. Many investors celebrate the nominal number climbing without checking what it actually buys them. This is the exact same distinction we explored with the Fed's broken thermometer, a headline number that looks like growth, sitting on top of a real, underlying value that might be moving in the completely opposite direction. Compound interest doesn't protect you from this. It just compounds whatever the real, inflation-adjusted rate actually is, for better or for considerably worse. Here's where compound interest stops being a friendly tailwind and becomes something genuinely dangerous, and the psychology here is worth sitting with. The exact same mathematics that quietly builds wealth in a savings or investment account works, identically in reverse, on debt. And in high-interest debt, credit cards being the obvious example, that same exponential structure destroys wealth considerably faster than it typically builds it in savings, simply because interest rates on unpaid debt tend to run far higher than typical investment returns. Here's the genuinely troubling behavioral finding. Research consistently shows people underestimate debt compounding more severely than they underestimate savings compounding. We're bad at intuiting exponential growth in general, but we're specifically worse at it when the exponential curve is working against us. The same blind spot that makes compound interest feel like magic in a retirement account makes it feel almost invisible, growing quietly in the background in a credit card balance, right up until it isn't invisible anymore. Here's a genuinely fringe, speculative idea, and I want to be upfront that this territory is far less established than anything else in this video. Some theoretical physicists and economists have experimented with modeling market dynamics using frameworks borrowed from quantum mechanics, where the evolution of a market state over time gets treated mathematically, similarly to how a quantum system's state evolves. In these speculative models, something resembling compounding shows up in how probability and value evolve together over time. I want to be clear, this is not mainstream, widely accepted financial theory. It's a small, active area of theoretical exploration, not something you'll find taught in a standard finance program. But it's worth including here as one more data point in this channel's larger thesis. Wherever you find continuous, self-reinforcing growth or evolution over time, whether in finance, in quantum mechanics, or in the biological examples we're about to get to, very similar mathematical structures keep showing back up across fields that, on paper, have almost nothing to do with each other. Here's a psychological trap that has genuinely cost people fortunes, and it's rooted directly in how badly human brains handle exponential curves. For any compounding investment held over a long time horizon, the overwhelming majority of the total gain, often 70 to 80% of it, happens in the final 20% of the time period. Early on, an exponential curve looks almost flat, boring, barely moving. It's only near the very end of the timeline that the curve suddenly, dramatically bends upward into what looks like an entirely different shape. This creates a devastating psychological trap. Most people, watching what looks like a flat, unrewarding line for years, quit investing before ever reaching the inflection point where the real growth happens. Our brains evolved to expect linear progress, steady, proportional payoff for steady effort. Exponential curves violate that expectation completely, hiding almost all of their reward at the very end, disguised as nothing happening at all for most of the journey. Here's a historical detail that explains why the formal mathematical study of compound interest took so long to develop, despite the underlying concept being thousands of years old. For centuries, both Islamic finance, through the concept of riba, and medieval Christian doctrine explicitly forbade compound interest, labeling it usury, considered morally corrosive, even sinful. This wasn't a fringe position. It was mainstream religious and legal doctrine across huge stretches of the world for an enormous span of history. This moral prohibition genuinely delayed the formal mathematical study of compounding until the Renaissance, when European mathematicians and merchants, operating in a gradually shifting religious and economic landscape, finally began rigorously formalizing the mathematics that ancient Mesopotamian lenders had been informally using thousands of years earlier. It's a striking example of a pattern we've explored before on this channel. A genuinely important mathematical structure, sitting dormant, held back not by any lack of mathematical capability, but by entirely separate historical, religious, and institutional forces that had nothing to do with the mathematics itself. Here's a nuance that most online compound interest calculators completely ignore, and it's an important one if you actually invest in anything beyond a fixed-rate savings account. In equities, mutual funds, or any investment with variable returns, what looks like compounding isn't quite the same clean process as compounding at a fixed rate. Because returns fluctuate year to year, what you're actually experiencing is path-dependent geometric growth, meaning the specific sequence in which good years and bad years occur genuinely matters, not just their average. Two portfolios can have the exact same average annual return over 20 years and end up with dramatically different final values, purely because of the order those returns happened in, a phenomenon called sequence of returns risk. A large loss early in the timeline, followed by strong growth, behaves very differently than the exact same numbers occurring in reverse order. Most simplified compound interest calculators quietly assume a smooth, fixed rate, completely glossing over this path dependence, a real, meaningful gap between the tidy formula and how compounding actually behaves in volatile, real-world markets. Here's a quick, genuinely useful mental tool named after physicist Enrico Fermi, famous for his ability to produce shockingly accurate rough estimates from almost no data. Most famously, estimating the yield of the first atomic bomb test using nothing more than falling scraps of paper and a quick mental calculation. Compound interest lends itself beautifully to the same kind of back-of-envelope thinking. At roughly 7%, money doubles approximately every 10 years. A simple, memorable checkpoint that lets you instantly sanity check any investment claim you hear without needing a calculator. If someone tells you an investment will turn $10,000 into $1 million within 10 years, a quick mental Fermi estimate tells you immediately that claim requires a return rate far beyond anything realistic, a useful, fast defense against exaggerated promises. Here's where this connects directly back to the pattern we've been building across this entire channel. The same mathematics, wearing a different costume, showing up across completely unrelated fields. Bacterial colonies, tumor growth, and the early spread of a viral outbreak all follow exponential growth curves that are mathematically nearly identical to compound interest. Explosive, accelerating, self-reinforcing growth, for as long as resources remain plentiful. And in every single one of these biological cases, the exponential curve eventually, inevitably hits a ceiling. Bacteria run out of nutrients. Tumors run out of blood supply and space. Viral spread runs out of susceptible hosts to infect. This is the biological mirror image of exactly what we opened this video with. Nothing in nature compounds forever, unconstrained. Not bacteria, not tumors, not viruses, and as we've established, not really money either, once you account for inflation, regulation, competition, and the simple non-existence of any financial institution that has survived thousands of uninterrupted years. The universe consistently imposes ceilings on exponential growth. Compound interest is not an exception to that pattern. It's simply one more example of it. Here's a genuinely strange, 300-year-old probability puzzle that connects directly to how badly human intuition handles compounding-like growth. The St. Petersburg Paradox describes a gamble with an unusual structure. A coin gets flipped repeatedly until it lands on tails, and the payout doubles with every consecutive heads flipped before that happens. Mathematically, the expected value of this gamble, the theoretically fair amount you should be willing to pay to play, is infinite because of how the doubling payout structure compounds. And yet, in practice, virtually nobody is willing to pay more than a very modest amount to play this game, even though the math says its expected value is unlimited. This gap between the infinite mathematical expectation and people's actual, modest real-world willingness to pay reveals a deep, persistent mismatch between exponential math and human risk perception. The exact same cognitive blind spot, 3 centuries old, that still causes people to misjudge compound interest today. Let's come back, honestly, to the claim in this video's title, because this is the most important, most carefully reasoned point in the entire script. Compound interest doesn't literally violate any law of physics in the real world, ever. In reality, every compounding process runs into financial speed limits, entropy like erosion from inflation, regulatory caps, competitive pressure from other investors chasing the same returns, and mean reversion, the persistent tendency for unusually high growth rates to eventually slow back down toward more ordinary levels. The phrase, breaking the laws of physics, is poetic, not literal. It's a way of pointing at something real and important. Exponential growth defies everyday human intuition so completely that, left running in a spreadsheet with no real-world constraints attached, it produces numbers that feel more like a physics thought experiment gone wrong than a plausible financial outcome. The math isn't broken. Our intuition for how far unconstrained exponential math can travel, left unchecked, badly underestimates the destination, and reality, mercifully, always steps in with a wall before we actually get there. So here's what I want you to actually walk away with today. Compound interest doesn't feel magical because it's supernatural. It feels magical because human brains evolved over hundreds of thousands of years to reason about linear, proportional relationships, steady effort, producing steady, proportional reward. Exponential growth is a fundamentally different mathematical shape, one our intuition was never built to naturally handle. And that mismatch is the real story hiding behind every eighth wonder of the world quote, whether or not Einstein ever actually said it. This is exactly why so many people quit investing right before the inflection point, why people consistently underestimate debt compounding worse than they underestimate savings compounding, and why a 300-year-old probability paradox still perfectly describes how badly we misjudge compounding-like structures today. The math is completely consistent. Human intuition is the part that keeps getting it wrong. If you've been with this channel for a while, this entire video should feel like a natural continuation of everything we've built together. Euler's number connects this directly to the same mathematics describing radioactive decay and quantum wave functions. The way exponential growth collides with real-world constraints echoes the exact same story we told about Fisher's conservation law equation, and about entropy quietly limiting Bitcoin's mining efficiency. And the psychological blind spot at the center of this video, brains built for linear thinking, confronted with exponential reality, is really just one more entry in the same running thesis this entire channel keeps returning to. Physics and money aren't separate languages. They're the same underlying structure, showing up again and again, wearing a different costume every time. $1, 5%, 2,000 years. More value than the observable universe. That number was never really about money. It was a mirror. showing you exactly how far human intuition breaks down the moment exponential growth is left running, without a wall to stop it. Real compounding always hits a wall. Your intuition, left unchecked, usually doesn't see it coming. If this kind of thinking, where physics quietly explains the parts of finance nobody else is willing to explain, is why you're here, subscribe. New videos every week, breaking down the hidden math behind money. See you in the next one.